there are three main things to think about.
Yeah.
Two of which you can control, one of which you can't, really. Right, you have got a Z80 processor, memory,
Yeah.
and lastly, you've got a chip called a ULA. And we can put this in a very simple way. The Z80 can be used to control the memory. The ULA reads the memory and outputs it to the world, right?
Mm-hmm.
In some form or other.
Yeah.
So that's pretty much how that works. And that is it, really, for the Spectrum. That really is pretty much it. I mean, you have got a beeper, I suppose. That's, you know, there are such things as we call ports, right? So
Yeah.
you've got a beeper, you've got joystick, yeah, okay.
Yeah.
So there are a couple of little things which are not directly controlled within the memory. I guess if you had a printer connected or whatever, but the outside wall, yeah, but still the ULA would more or less handle those as well, right? So how does the memory work? Well, if you imagine there's just a big load of silicon, and within that silicon you've got the ability to have a sort of a high or a low voltage. Yeah. I think that's how it works. And these are stored in chunks of 8. So little switches, 1,
Yep.
2, 3, 4, 5, 6, 7, 8, right? Okay, like this. We'll put a filler in here, just to give it so we can see, right? Any particular color, right? Let's just use that one. Okay. Yeah. So
Yep.
that's a single little tiny slice of silicon, right?
Yeah.
And it's in a group of 8 like that. So, and each one of these can be either on or off.
Mm-hmm.
And so we can set it like that to be either 0 or 1, right? Like a little switch.
Yep.
So you can imagine if you start here with this one, there are 2 possible combinations. It's either on or off, right?
Yep.
So if I fill that one like that to be on, let's say, okay, now it's on, right?
Yep.
Or off. If you go and use 2, how many combinations?
What, those 2?
Yeah.
4.
Yeah, of course, because you can have both off.
Yep.
You can have that one on. You can have that one on. And you can have both off, right?
Yep. Yep.
So in that sense, you've now got 4 possible combinations, and if we give those a number, combination 0, combination 1, combination 2, and combination 3, right?
Yeah. Yeah.
Okay. Now, that is what we would call a 2-bit number, right? 2 bits. Total possible combinations is 4, right? Easy enough.
Yep.
Okay. Now, if we place a value on this column of 1, yeah?
Yep.
And a value on this column of double that, which is 2, yeah?
Yep.
Then you can see that if we add these together, that means that's a 1, that makes 1. That's 2, that makes 2. Both together, 2 plus 1, that makes 3, right? So you can see it's simple enough. That's 2 bits, right? So logically speaking, if we then go and add another column like that, how many combinations now? It's actually pretty logical, because here there were 2, here there were 4, so here there must be Every
Not 8 though, is it?
It's 8. Of course it is 8. Yeah. Every time you add
Okay.
another switch of 0 or of 2, you're going to double it, right?
Okay. Right. Yeah.
Yeah. If you think about it, look. Let me show you why that's really logical, right? Because let's say here you've got 4 combinations, right? Yes? Clear?
Yeah.
And so, logically speaking, then there must be a set where this one is off, and another set where it's on, right?
Right.
See what I mean?
Yeah.
So logically there, you can see that must be 8 possible combinations. That makes sense?
Yeah.
Yeah? We losing you a little bit, or are we okay? One,
2 combinations there.
2.
4, yeah. Okay. Yeah. Yeah.
1, 2, 4, right?
Yeah. Yeah.
And so let's go, and we can see here. So here we got nothing, so that's 0. This one, if we read down here, that's a 1.
1. Yeah. Then 2. Then 3.
1 and 2, then 3. That one is a 4. That one is 5. That one's 6 and 7. No, we don't have 8 because we've got 0 to 7, right? If we did want to have an 8, we'd have to double again.
Yep.
And then add another row like that. And so we'd have to replicate this whole thing again like that, right? And then I'll just put it over here just for the sake for argument, right? I'll put it over, just let me resize because it's going to get confusing. And so I'll replicate that a second time, and we'll have one set where those are all off.
Yep.
And this time there's going to be 8 of them, not 4. And then we'll have another set where these are all on. 1, 2, 3, 4, 5, 6, 7, 8, right?
Mm-hmm.
So you can see this, you can start to see this, there's a pattern emerging here, right? Because you can see this goes off, on, off, on, off, on. Yeah, and this one goes off, on, off, on.
Yeah.
And then this one goes off, on 4 times, and then this one goes 8 times, right? And you can see that
makes sense.
That shape is all emerging there, right? And now we've got value 1, 2, 4, and 8, right?
Yep.
Giving us a total combinations of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right?
Yeah.
So that is more or less how it is stored in the actual silicon itself, right?
Okay.
Switches on and off so that you can read a number. And in this case, this is what we call a 4-bit number, also called a nibble. And as you can see, a nibble can have a value from 0 to 15. And in very early computing, that is what they used, right?
Okay.
Now, what we often do with that, as you may remember, is because that's a nice chunk, we don't actually, we instead of going 10, 11, 12, 13, 14, 15, we actually store these as we record them as A, B, C, D, E, and F. So we just sort of imagine, instead of working with 10 numbers, we're working with 16 numbers. That's why we call it hexadecimal. And hexadecimal is a shorthand way of having 16 codes that can each one can represent 4 bits like that, right? Yep. So F is represented here by 1 1 1 1, and so on, right? 0 0 like that, right? So that's essentially how we can deal with, because we don't want to deal with one bit at a time. It's very, I mean, that is exactly how the computer deals with it completely. That's why, you know, it looks a little bit like a punch card, right? Because those punch cards used to do exactly that, right? To represent those numbers. But for a human, that's not very convenient. At the same time, if we start using decimal, it's kind of like, it's easy for the human, but harder then for you to kind of translate back to the machine. So the hexadecimal is a nice, easy way of a kind of halfway between human readable and the machine readable. Yeah?
Yeah.
But of course, for the machine, it really is just dealing in, it's not even dealing in numbers, it's dealing in ons and offs, really.
Yeah.
So that we go 8, and then we go 16, and we double 32, and we double 64, and we double 128, right?
Yeah.
So, and what you can see there is, look, there's a group of 4 here, and there's another group of 4 there, and that will give us, if we add all those numbers together, if you imagine that the very 255,
it's too far.
right? So 0 up here, and I'm not going to draw 255 of these things, but there, from there all the way to 255, and that we call an 8-bit number, right? And everything that we do in the Z80 is in 8-bit numbers. You'll hear that sometimes we talk about 16-bit numbers, right? But really, we're just joining two 8-bit numbers together, right?
Yeah.
So the same way here, right? You can join a 4-bit number, and then you can just tack another one on there, and you get an 8-bit number, right?
Right.
So you can, of course, just then tack another group of 8, and you'll get a 16-bit number. But we'll come to that in a minute. So right now, there you can see we can use two what we call nibbles. And if I, for example, then, let's give you an example, right? We'll just pick a random one here, and we'll put that over there. I need to just make this adjustment as well. Again, I'm getting a bit out of space. Okay, so I've just picked a number there. Which one was that? 3, yeah? Okay, and pick another one there, and I'll put that here, right? So now I've got an 8-bit number, right?
Yeah.
But the nice thing about hexadecimal is that it's actually really easy to understand what that number is, because these 4 here still represent a 3, and these here would still represent B, right? You see how that pattern matches there? This one here matches to that one, and that one matches to that one, right?
Yeah.
So although in decimal, sorry, in binary, the number is 0 0 1 1 1 0 1 1, right?
Yeah.
And then, but in hexadecimal it's just 3B. Now in decimal, it's hard to translate directly. That's why it's good to get in the habit of using hex, right? But what we do know is that it would be 1 plus 2, no 4s, plus 8, plus 16,
32.
plus 32, right? And presumably, if I'm using Excel here, I can just do a sum of those numbers like that. And you can see there, it says 59, right? So that's what it would be in decimal. Now, interestingly, if you look at this, you can actually figure what this is what this thing is, because 3 here means 3 times 16. Do you understand why?
Yeah, because that's the that starts at 16.
Yeah, and that's the high. That's what we might call the high nibble. Let's say, right? Yeah, just in the same way as if you have a number in English in decimal, like say 1, 2, 3, 4, right? 1,234. Then the 2 there is 2 hundreds.
Yes. Yeah.
So in this case, it's like this is the number of 1s and this is the number of 16s.
Yeah.
So you'll see, if I say then 3 times 16 is 48, yeah?
Yeah.
And B, well, we know B is 11, right?
Yep.
So 48 plus 11?
59.
59, right?
Mm-hmm.
There you go. So, okay, so that's how we can represent an 8-bit number in binary and hexadecimal. I think you've got it. Is that all fresh now?
Yep.
Good. Right then. So, now, we can store an 8-bit number in memory by giving it an address, right?
Yeah.
So, addressable memory is a system by which you can basically tell the CPU where to find a particular number, let's say, right? Now, if you were to use an 8-bit, if you were to use only 8 bits, then you'd only have 256 possible addresses. Yeah?
Yep.
Think of it like a street. It'd be like a street like that, right? And each one of those would have a number in it. And it'd be a big long street like this. And it would go on. It would go on like that. And we'd start with. Let me just fill it with some other color. I like using these colors. We'll use green. Okay, right. So you'd start off here.
Yeah.
You'd start off with 0, 0, and then you'd have. Just a minute. Let me just write like this. You'd have 0, 0, and then you'd have 0, 1, 0, 2, 0, 3. Yeah, and you'd go all the way up to FF, right?
Yeah. Yeah.
At that end, like that. So you'd only have a total memory of 256 bytes that are addressable, right?
Yeah.
And those early computers, they really did just have that,
Yeah.
So anyway, they said, well, look, you know what? That's really not enough, is it? I mean, 256 bytes, not very much at all. It's a quarter of a K. So how are we going to solve that problem within 8 bits? Well, essentially, the way that you solve it is that you take your 256 like that and you say, okay, that's a page, right?
Yeah.
And then what we're gonna do is we're gonna have a whole, several rows of pages like that. So let me just show you that. Let me just choose a different color there, just so we can see a difference, right? Okay, like this, right? Like that. Now imagine that stretching out 256 all the way, like that, right? Now each of these squares can hold a number of 8 bits, yeah.
Yeah.
And the way that we address it, it's like a street number along here, a street name here, and a house number along the horizontal here, right?
Yeah.
So we'd go, 0, 0, and then we'd have 0, 1,
Yep.
0, 2, 03. So, and each of these, each one of these is 256 addresses, right?
Yes.
So if we went all the way down to FF down here at the bottom, then you'd know that we'd have 256 rows of 256 addresses, giving us 65536 total, which is also we call 64K total possible addresses, right?
Yeah.
And in order to address that, we use, as I say, it's like the house number here. We call it the low byte, right?
Mm-hmm.
And then the high byte is like the street name, or we can call it the page number. It's the row, right? So there are 256 in each row. So each one of these actually represents 256. So that would be 256. That would be 512. That would be 768. That would be 1024, right?
Mm-hmm.
And then you would add that number to that number, and then you would know the address. But because it's in hexadecimal, it's super easy to know an address because you literally just have the high byte and the low byte, right? So if you want to point to any one of these little chunks of bits like this, you can address it using a high byte and a low byte, right? So for example, the screen memory is at 40 high and 00 low.
Yeah.
Yeah?
Yeah.
40 high, 00 low, just like that. And so any address in the code can be described with two 8-bit numbers. And the processor will use those in combination in order to allow the Z80 to address, read, or write anything in the memory.
Yeah.
Okay? So if you look at this, right, let's go back and look at this address, 40, right? So that's a pretty easy number to represent on our little sort of table here. So we've got 4. This would be so the 4 would be here, right? This would be our hex number here. So that's 1, 2, and that one is 4. So the number would be that one there, right?
Yeah. Yeah.
And 0, of course, obviously that would just be 0, right?
Yeah.
Like that. So that's 40. And then the other address. The other address would just be all zeros, right? Like that.
Yeah.
Okay. So if we count back, we can say, okay, so we've got 1, 2, 4, 8, 16, 32, 64, 128, right? And then here, because this is a high byte, right? So to know the real value of this byte, it's going to be, we're going to have to multiply it by 256, right? See what I mean?
Yeah.
Sure?
Yeah, this
1,
is where
2,
I think
4.
last time we did this, we maybe either didn't go over this or didn't explain it because
I don't think I probably didn't explain it as well. I feel like I'm explaining it fairly well.
Yeah,
now.
you are. Yeah, it's much better because I was wondering like how you get the much bigger number.
Yeah.
So yeah.
Yeah, right. So we know that one is representing 64.
Yeah.
But because it's a high byte, we also then going to multiply it by 256.
Yeah.
Yeah?
Yeah.
In the same way as like in decimal, if you had 1,000 and 1,000,000, right? Then you're going to go, okay, well 1,000,000 is multiply it by 1,000 again. 1,000,000 is 1,000 thousands, right?
Yeah. Yeah.
So like 0, 0, 0, 0, and then another set of 0 like that. It's 1,000 thousands, right?
Yes.
And so it's the same principle, but instead of 10, 100, 1,000, we're going to do 16, and then 256, because it's multiplied by 16 each time rather than 10. Right, so 64. So if we go 64 multiplied by 256, it's 16384. That's what it is in decimal, right?
Yeah. Yeah.
And so that's an address that we can write to, and we can do that in BASIC easily enough, as we probably have done before, right? So I'll go over to the 48K BASIC, right? And I'll go poke. Now, let's say we pick a number that we want to poke to that address, right? So we'll pick an 8-bit number, right? Let's pick an 8-bit number. We'll put it down here. Again, so we should be able to do this pretty easily. Let's do a little something like that, right? A little pattern. And we'll go 1, 2, 4, 8, 16, 32. Have I done 9? I think I might have. 64. 1 to 8. Right? 1, 2, 3, 4. Yeah. So forget that one. Ignore that one there. That one's nothing. Right. Okay, so we want to put that pattern in there. So let's add it up, right? So it's 2 plus 8 is 170.
Yeah.
Okay, so if you poke, look at the spectrum now, and you poke 16384, right, with 170.
Yeah.
And there you can see ... right?
Yeah. Yeah.
And if you do 171,
yeah,
then you're just going to add a 1. You're just going to light up that one little bit at the end there.
Yeah.
And if you watch the screen, you'll see it. That one little bit will just change there. Do you see it? Boom. Just like that.
Yep.
And if you added 4 to that, 175, then you see it'll start to fill it in, right?
Yeah.
Okay. So, and that, as you can see, is 8 pixels on the screen that we're controlling with one write to memory.
Yeah.
So what that tells you is when you're controlling the screen for graphics, you're always working with 8 pixels at once, right?
Yeah.
At any time when you're writing, when you're drawing a sprite or you're writing a font or anything, you've got to do it in 8 horizontal pixels at a time, right?
Yeah.
Now, we've gone through before how the spectrum memory works, and we know that it's quite unusual, right?
Yes.
So, I'm not sure if I can remember how to do this. I can't remember the basic codes. But if you did a loop where you were writing from memory in order from 1, 6, 3, 8, 4, 5, 6 all the way across, you're going to see it's going to look like the way that a screen loads, right? So it's not totally linear, right? There is a video. I've done a YouTube video on it, right? So if you want to watch that to understand how it works, it'd probably make more sense now after that explanation. Anyway,
I think I remember that from the last time. But
yeah. So the screen is split into 3 segments, and it's written so that you've got a sort of the top lines are done first, and then the second line, and then the third line, and the fourth down to the But it's a bit of a mess. It's a pain to deal with, but that's what it is. Okay. Anyway, a quick calculation on Excel. If you imagine the screen. Yeah. So we know we've got 32 characters across, right?
Yeah.
And we know that it's 8 pixels per character, so the resolution is 256, right? So it's 200. So to do a 256 pixels across, you're going to need 32 bytes all the way across one line.
Yeah.
Now the TV screen is 4:3 ratio.
Yeah.
in the old days, 4 to 3, right? Which tells you 256 in a 4 to 3 ratio would be 256 times 192.
Yeah.
So we've got 256 pixels across, 192 pixels down.
Yeah.
So a grand total number of pixels on the screen of 49,152. And we're representing those pixels in 8-bit chunks. So if we divide it by 8, that tells us how many bytes we need to have a 1-bit image on the screen. And the answer to that is 6,144 bytes. Yeah, makes sense?
Yeah.
A lot of this stuff makes a lot more sense when you look at it in hex as well. So I think the code for the, is it dec to hex? It is. So I'm going to write dec to hex here. That's going to tell me the hexadecimal. And then you'll see how much more round those numbers are when they're in hex. Yeah? You see that?
Yeah. Yeah.
So, yeah. So the screen memory, as we know, it starts at 400.
Yep.
400, right? And the pixel memory will obviously finish. We know the size of the pixel memory is 6144, right? So if we add 16384, that's where it starts, to 6144, we get 22528, right?
Yeah.
That's going to be the end of the screen memory. In fact, the end of the screen memory is 22527, right? Because it's 0 to right.
Yeah.
Okay, so the last number in screen memory, 22527, as you can see there, 57FF. Let's poke it, right? Let's just poke it as a little test. Now, what I'm going to do is I'm going to poke it in BASIC, because the command line will destroy what we've done if we don't do it this way, right? So 22527, I'm going to poke it with 255, which is a full black line of 8 pixels, yeah? And then I need to pause, right? Pause 0, that's wait for a press a key.
Yep.
And there it is, right? There it is, right at the bottom of the screen. You see it?
Yeah. Yeah.
And I will press a key and we're back. Okay, so what happens if we go to 22528?
Now we're into attribute country.
Well, there we go. So 225 attribute country. What a place. So if I poke 22528 with 0 and run it, what do we get? There. Ink 0, paper 0, flash 0, bright 0, flash 0, right? And so we've written to memory there as well.
Yep.
Okay, so that's all clear and logical, right? So now we know how to address the memory, right? Now the Z80 has a means of doing that, which we can talk about. But before we do that, I actually want to talk to you about something slightly different, which is how the ULA interacts with the CPU.